Everybody, I'm going to talk a little bit about the thermodynamics of the radical halogenation reactions in this video. So this is kind of going through the couple sections in your book that talk about really kind of the thermodynamics and how these reactions are actually able to be spontaneous. So first off, we just need to remember about delta G here. Oh boy. Okay. All right, so delta G, it's made up of the enthalpy and the entropy terms. So in this particular case with these radical halogenation reactions, since we're starting with two molecules and ending with two molecules, we can essentially assume that that entropy term is going to be negligible because we've got kind of the same amount going in as going out. So the entropy is not going to be a really big factor in this reaction. So our Gibbs free energy basically boils down to this, where our delta G is going to about equal the delta H term, okay? So we're really particularly looking for a delta G to be negative, in which case we're going to have the products favored. It's going to go spontaneously in that forward direction, okay? If we have a positive delta G, that means that we're going to favor the reactants, and that reaction is not really going to go on its own. Okay, so we want to talk a little bit about why these radical reactions actually work, because it seems like they go through some high energy stuff in the middle. So we want to just think about what bonds we're breaking versus what bonds we're forming here. So in the green, I've got the CH bond is one of the ones that's getting broken, as well as the halogen bond, so the bromine-bromine or chlorine-chlorine. And then on the other side with the products, we're forming a carbon to halogen bond and an H to halogen bond, okay? So when we're looking for the delta H of this, we're really looking at bond dissociation energies, and they give us a really, really good look at the radical processes, because the bond dissociation energy is just the amount of energy needed per mole of basically splitting a bond perfectly in half, which is what a radical reaction is all about. So we're looking at kind of that bond strength and thinking about, you know, if that bond is easy to break, we're going to have a lower bond dissociation energy, okay? So these are kind of bond dissociation energies of a handful of relevant bonds here, because we're really looking at the bond dissociation energy of the bonds broken as a sum, and then subtract the sum of the BDE of the bonds formed, okay? And then depending on whether that's negative or positive, that gives us an idea of whether or not this reaction is favored. So table 10.1 this is just from your textbook. So I kind of want to go through a little bit of this. I would say if you kind of look down the periodic table here as you go fluorine, chlorine, bromine, iodine, we know that we're decreasing in electronegativity. We know that we're increasing in size, okay? So that being said, when you look at this column in particular, it looks a little bit weird because there's a pretty clear trend among these three bond dissociation energies that as we go down the periodic table, we have those bonds getting longer because our atoms are getting larger. It's becoming easier for that bond to break because once you have a really long bond, it's easier to break that bond apart. And you're going down in electronegativity, so you're getting to a point where, you know, having not a full octet of electrons is not, you know, the end all be all of the process here. But when we look at the first couple of halogens, the fluorine compared to chlorine, that 159, that's a really, really easy bond to break. Okay, so when we're looking at this trend, we kind of want to think about the fact that when we've got fluorine and fluorine here, we're looking at something very different than when we're looking at the rest of the halogens. Okay, so in this case, our fluorine atoms are actually so small that this bond is too short. Okay, because it's so short, you're actually getting repulsion from the two fluorine atoms that and they're trying to get away from each other because they're getting to a point where they're actually too close in space that all their, you know, electron density around them is starting to push away from itself. Okay, so this repulsion is what's leading us to this kind of weird outcome, where as soon as we go down to chlorine, we're going like way, way up again. And so this is going to be kind of the trend that you would expect. Okay, we're getting larger atoms. And longer bonds. So they're easier to break. Okay, as we go down the periodic table. So we're going to use these bond dissociation energies to look at the exothermic or endothermic properties of the 4 different halogenation reactions. Okay, so we want to keep in mind here, we're looking at the sum of bonds broken, sum of bonds formed, and those are subtracted from the bonds broken. So first off, we want to think about, so for fluorine, okay, we're looking at the CH, so 435 of methane, and then the bond dissociation energy of fluorine, and both of these two numbers added up, and then both these two numbers added up, and then you subtract one from the other. So this is the math. You can go through it if you want, but I just put that in there so that you kind of see where the numbers come from. But if we look over here, this is kind of the important stuff. This is the delta H of these various reactions. So if we look here, this number is like crazy large, okay? So there is a ton of energy being released in that fluorination process. This is so exothermic. It's actually dangerous, okay? So let me see if I can, there we go. So this is such a violent reaction that nobody does it because it is just not safe to perform, okay? So when we get to chlorine and bromine, these are both exothermic reactions. We can see that chlorine is significantly more exothermic than the bromine is, but that is mostly going to end up in terms of rate. And we'll talk about why this difference is actually important as well. These are both good to use. And then if we look down at the iodine one, this is actually endothermic. Okay, so this one actually won't proceed spontaneously without like a lot of heat being added. Okay, so because of that, that's also a situation where it's just not very practical to run a radical iodination. But the chlorine and the bromine are worth a little bit more analysis. So let's go ahead and talk about chlorination versus bromination. And so this bond dissociation energy table is actually from chapter 6. It is page 235 in your textbook. Okay, it is longer than this. I only have a little section of it in here right now, so I kind of have like the first chunk of it, because that's the main part that I needed here. So the bond dissociation energies of common bonds, it gives you, so where this table just sticks with methane, this talks about other types of hydrocarbon bonds. Okay, so it has a whole bunch. It also has a whole bunch of kind of, you know, like carbon to halogens of different types of carbons. It's got all the XX ones. It's a nice big table if you kind of want to look at this math a little bit more carefully. But I have this in here so we can particularly look at the ethane example here, where we're specifically looking at this side. Okay, so we're looking at that guy. The bond dissociation energy of CH on ethane is 410 kilojoules per mole. Okay, so we're just going to look at bromination versus chlorination. of an ethane, okay, ethane is going to be a little bit more of a typical example than if we were looking at methane. Okay, if you look at the methane ones, it's a little bit weird, but not really many people actually do a halogenation on methane. It's more common to do it on some kind of more complicated hydrocarbon. So this is going to be a better overall view of kind of bromination versus chlorination reactions. So we want to just kind of look at the two propagation steps. So we're not really looking at initiation. We're not really looking at termination. These two propagation steps is where most of our, all of our rate determining steps occur. That's where our product is formed. So we're going to look more into those. So this first step, which is the radical, the hydrogen atom abstraction, that first step is going to be our rate determining step. Okay, so we're going from some sort of halogen radical to a carbon radical. So the really interesting thing about this is that if you compare this bond dissociation energy to this bond dissociation energy, so we've got something that's 410 kilojoules per mole from right here. Okay, so we're looking right here. And then 431 for that HCl bond. Okay, so when you look at those two, if you take 410 from our bonds broken and then subtract 431 for our bonds formed, we're getting to -21. Okay, the fact that that is negative, that is going to be an exothermic process. Okay, that's actually kind of an interesting outcome, considering the fact that that really means that the chlorine radical is less stable than the carbon radical. Okay, so we're actually going down in energy when we go to that carbon radical. So when we have bromine, okay, so we start with a bromine radical and we do our hydrogen atom abstraction to get to our carbon radical and HBr. So we're still looking at the same bond in terms of CH, bond dissociation energy. But now we're looking at the formation of HBr, which has a BDE of 368. So when we're looking at that, that gives us a delta H for that particular step of +42. Okay, so that's actually an endothermic process. Okay, so we have to, energy has to be put into the system to be able to go from this with bromine to that with bromine. Okay, but in the chlorine version, that step is exothermic because we're going down in energy. But if we look at the second step, where we now have halogen abstraction, where we're reforming our propagating radical, forming our product. So we're looking at breaking that halogen bond and forming that CX bond. And again, I got the numbers for this CX from that table on page 235. I think I just I don't have it on this page right now, but if you check it out, that's where these numbers came from and things like that. So the bond dissociation energy of that Cl-Cl bond is 243. And then the carbon chlorine CX bond is 339. So when I subtract those, I again have another exothermic step. Okay, if I compare that to the bromine version, splitting BR-BR has a bond dissociation energy of 193. And then that CBr bond, that is a bond dissociation energy of 285. So when I look here, I'm still having an exothermic step in my second step of my bromination. Okay, so if we look at the overall delta H for chlorine, I essentially have two exothermic steps. So I have something that's very exothermic in the end. Let's write a little bit more. And when I look at my bromine version, I start off with an endothermic step but then my exothermic step is so exothermic that I still have overall an exothermic process. So it's still favored for the bromination. It's probably just going to be slower because that first step is going to take some time to get over that higher energy barrier. So if we look at the reaction coordinate diagrams of this, so if we look at chlorination, okay, we start off with something where we're definitely starting off higher in energy. Okay, so we've got some kind of and we've got our chlorine radical, and all of that is just pretty high in energy based on our data that we have. So when we go up and over, we're going down into that carbon radical plus HCl. Okay, so all of that is going to be lower in energy. That step is exothermic. And then we do our final step and we go way, way down, okay? Overall to get to our final product, which is the alkyl halide and our HCl, okay? So if we compare that to bromination, for bromination, our starting kind of, the starting point of our propagating set with our alkane and our bromine radical is much, much lower in energy, okay? So that means we have quite a high climb to go to our first intermediate where we've got now our carbon radical plus HBr. And then it's just a little bitty bump to get to overall something that's lower in energy to our final products. Okay, so it's still exothermic, not as exothermic, but this initial step is very endothermic, whereas this one is exothermic. Okay, so we're looking at it in a very different light, where this, no matter what you do, is going to be releasing energy. Okay, this one, you're always going to have to kind of push that along. Okay, so let's write up a couple of conclusions here. So the interesting thing here is the chlorine radical is less stable than the carbon radical. Okay, so that's going to give us a whole lot to think about when we think about the selectivity of this process. That really got out of control. Okay, so when we're thinking about that, we want to consider that chlorine is more electronegative than carbon or bromine. Okay, but it's not as large. Or the iodine. Okay, so it's weird to think about the carbon radical being more stable, but chlorine is more electronegative. It's not as big, so it doesn't have as much going for it as the other halogens do. So it's more electronegative than carbon, so it wants those electrons more. So it's happier to get those electrons back and then make carbon more miserable. But when we come to bromine, the bromine radical is more stable than the carbon radical. Okay, so when we're looking at that, bromine would rather have that radical than carbon because the bromine is less electronegative than chlorine. Okay, so we're going down, but it's also a larger atom. so it can stabilize that radical better. Okay, so it's kind of weird things, but we're thinking about this in terms of how stable are the radicals that we're forming. So if we look at how this actually affects stability and product formation selectivity, and when we're looking at chlorination, because we're starting off at such a high energy level, and because we're going down in energy so much for that very first step where we're forming our carbon radical, there's not as much preference. There's not as much preference up here, because it doesn't matter what carbon radical you're going to, it's still going to be lower in energy than the chlorine radical that you start with. Okay, so that leads to these energy of activations are quite similar. Okay, so if I go, a little higher and go to a primary radical, that's not that much different than if I do the secondary. Okay, so chlorination does not have very good selectivity. Because we don't have good differentiation at that rate determining step. RDS transition state. Okay, so one of the things that your book mentions, it talks about the Hammond postulate a little bit, and that's the idea of kind of this energy level is pretty close to each other. So our transition state here is going to look more like this. So we're not going to have as much radical character on our carbon yet. So there's not as much to kind of push it one way or the other. Okay, so we're not going to have good selectivity here. On the other hand, when we've got bromination, we have, this is going to be a lot closer to our product. So our transition state here is going to look a lot more similar to the carbon radical than it's going to look to our bromine radical. Okay, so that means there's going to be more radical character in our carbons in the transition state. So that transition state is going to be able to kind of push towards the more stable radical because there's more radical presence there, really. So we kind of look at like how big this is. Fix this. Okay, we have a much bigger difference between the energy of activation of these different options. So our bromination is much more selective for the more stable radical. Okay, and a lot of that is thanks to this endothermic process compared to this exothermic process. Alrighty, so as always, let me know if you have any questions, and hopefully this kind of cleared up some stuff with that thermodynamic math portion of the radical chemistry.